Thousands of meters below the ocean surface, high-temperature, metal-rich hydrothermal fluids violently discharge into freezing seawater. Beneath these active vents, dissolved metals precipitate out of the superheated fluid, cooling and accumulating into highly complex, vertically zoned massive sulfide lenses. But these deposits rarely stay neatly exposed on the seafloor. Millions of years of tectonic activity uplift, fold, and deeply bury these massive sulfide systems beneath thick sequences of varying host rock. Hunting for these buried volcanogenic massive sulfide, or VMS, systems presents a severe diagnostic problem. Because they are structurally controlled and completely obscured by massive volcanic piles, single-discipline exploration methods generate an overwhelming number of false positives. To find them, we deconstruct the 5 primary genetic models of VMS deposits. By stacking their unique geochemical, geophysical, and structural signatures, we can rank potential targets based on the specific signatures of the hydrothermal system. Modern exploration requires us to ignore isolated anomalies and instead track the entire thermodynamic footprint of the VMS system. This matrix maps the 5 main genetic models of VMS deposits. The tectonic environment dictates their physical architecture and metal endowment. Starting at mid-ocean ridges, the Cypress-type model forms in back-arc oceanic settings, yielding a distinctly copper-rich signature. The host rocks here are oceanic basalts and ophiolites, featuring prominent pillow lavas formed directly on the ancient seafloor. Moving to rifted back-arc basins, the host rock shifts. The Beshi-type system forms within mafic volcanics mixed with deep-sea siliciclastic sediments, generating a unique copper, zinc, and cobalt signature along the sedimentary contact. In island arc settings, the chemistry becomes highly polymetallic. The Corico-type model sits in bimodal felsic host rocks, like rhyolite, and carries immense concentrations of zinc, lead, copper, silver, and gold. The resulting ore from these felsic environments is dense and complex, often capped by massive barite and silica. By contrast, bimodal mafic systems, like the Noranda type, develop thick volcanic piles. They lack the high lead of the Corico type, but produce strong, easily identifiable copper, zinc, gold feeder pipes. Finally, in continental rifts, the Bathurst type forms massive silicically hosted horizons. These are giant deposits dominated by zinc, lead, and silver, with very little copper. Historically, we found these systems by tripping over their exposed surface expressions or finding ancient workings in the hills. Today, establishing the regional tectonic setting is our mandatory first step. It dictates which chemical and physical anomalies we must hunt for deep underground. This cross-section illustrates the internal fluid dynamics of a VMS system. The severe temperature gradients from the vent to the seafloor create highly predictable elemental halos. At the outer edges, we find the distal exhalative halo. Barium, manganese, antimony, and thallium map the system's outer limits, furthest from the heat source. Moving closer to the heat source, the main ore horizon forms. Here, elevated levels of zinc, lead, and silver concentrate into a massive sulfide lens. Plunging directly into the highest temperature zone reveals the chloride-altered feeder pipe. Copper, iron, and cobalt precipitate directly inside this vertical conduit. Absolute metal concentrations in surface samples are often skewed by local background levels or soil dilution. To find the core hydrothermal plumbing, we look past absolute values and instead analyze the relationship between specific elements. The copper-to-zinc ratio is our primary vector. Because copper requires much higher temperatures to precipitate than zinc, an ascending copper-to-zinc ratio points directly toward the hydrothermal vent. We also track the iron-to-manganese ratio. A rising value here separates the intense hydrothermal fluid path from the surrounding distal sedimentary background. Tracking the shift in these ratios allows us to map the transition from distal halos to the feeder zone, regardless of absolute surface grades. Geochemistry points the way, but geophysics maps the physical reality of the blind deposit deep underground, relying entirely on density and conductivity contrasts. This graph shows a gravity residual high. Massive sulfides, densely packed with pyrite and galena, universally present as heavy, localized anomalies against the lighter volcanic host rock. By applying a first horizontal derivative, or FHD, to this gravity data, We calculate the exact vertical boundaries of the anomaly, mapping the synvolcanic fault structures framing the ore. Magnetic signatures require a different approach because their responses completely invert depending on the genetic model we are targeting. In copper-rich mafic systems, like Cyprus or Naranda, the footwall alteration zones are packed with pyrrhotite and magnetite. This generates strong magnetic highs directly beneath the vent. But in felsic zinc-lead systems, like Curacao, the intense sericite alteration actively destroys the background magnetite. The result is a sharp, localized magnetic low over the ore horizon. Finally, to confirm the presence of connected metal, we measure induced polarization. The disseminated sulfides residing in the feeder stockwork yield massive, unmistakable chargeability spikes. Interpreting a magnetic low as barren rock or a gravity high as an automatic target is impossible without first defining the genetic model. Applying these datasets across hundreds of square kilometers of rugged terrain requires a systematic, layered filter. This regional grid allows us to synthesize the independent geological, geochemical, and geophysical datasets into a single target area. Step 1 isolates structure. We extract intersecting synvolcanic faults and lineaments pulled directly from digital elevation models and Sentinel-1 radar data. Step 2 maps alteration and density. We overlay Sentinel-2 multispectral anomalies to locate the chloride and sericite halos, then align them tightly within the gravity, FHD, and magnetic boundaries. Step 3 verifies the sulfide. We check the deep IP data for chargeability spikes above 50 millivolts per volt, confirming the presence of metallic bodies within that strict density boundary. Step 4 applies the geochemical vector. We verify that surface sampling over this exact nexus shows the ascending copper to zinc and iron to manganese ratios pointing straight down into the crust. By identifying where structure, density, and chargeability intersect with increasing metal ratios, we isolate the site most likely to host a concentrated VMS ore body.